Hey everyone, at this point you should have completed section 7.1 through 7.4, which means that you've now learned all the integration techniques that you're going to need for this class, right? So what do we have? We have integration by parts, products of trig functions, trig substitution, and partial fractions combined with u substitution. So those 5 techniques together make up the integration techniques that we need to know for this class. Now today it's not going to be a traditional lecture. There's no new material to learn. What we want to do is talk about strategy for integration. And the point is, antiderivatives are much more difficult than derivatives. If you have some function and you need to differentiate it, you just do it, right? You look at it, you say, oh, it's a product, I need the product rule. Quotient, it involves exponentials or logs or inverse trigs. We know all the formulas and the rules, like the chain rule, for taking derivatives. It just doesn't work out quite as nicely for antiderivatives. Antiderivatives are more difficult than derivatives. Now, to get started, you will definitely, and we have an exam coming up on, I guess it's about a week and a half from now. And so you will definitely need to know the standard integral formulas. So know formulas 1 through 14 on, it's page 543 of your book. So you absolutely need to know those formulas. And let me give you the ones that I want you to know that involve, or that are connected to the inverse trig functions, right? Integral of 1 over square root of 1 plus x squared, that's going to be an inverse sine x plus c. You need this one, and I prefer to state this one in the more general format. 1 over a squared plus x squared dx. Right? And that one is the inverse tangent, or involves inverse tangent. It goes like this: 1 over a inverse tangent of x over a plus c. And then one more, right? That one is 1 over x times square root of x squared minus 1 dx, and that one's equal to inverse secant. So inverse secant of x plus c. So these 3 formulas are worth knowing, and I like to give this one in the more general format because it comes up more often. The other 2, if I see some number other than a right here, I can just factor things, and I hope I'm not losing the shot here. Let me just fix this. I just realized that my camera wasn't quite centered. Anyways, if there's some other number, if there's a 4 right there, I can factor things and do a quick u substitution to figure out what the adjusted formula is. So I've never memorized the more general formula for this one or this one, but this one I think is worthwhile. So, you'll also need to know your trig identities, right? Because you can't do products of trig functions without knowing your trig identities. So know your trig identities. Which I labeled as 1 through 6 when we just discussed them. Now, here's one of the things that you should expect, especially on quizzes and exams coming up. What you're going to get are problems where, first of all, it's not going to tell you use this technique or use this technique. Sometimes you can actually use more than one technique, but even more, let's say, interestingly, so you can expect to use more than one technique when computing or on a, let's say, on a particular problem. I mean, maybe the classic example of that is when you have a trig substitution problem. You do a trig substitution, and what does it do? It brings you to a product of trig functions, so you need to know how to integrate products of trig functions. But more often, or more generally, you can have a situation where you have a problem that asks you to compute an integral, and what do? You do a u substitution, and that gives you an integration by parts problem. Or vice versa, sometimes you do an integration by parts, and then to complete the next integral, you'll need to do a substitution. So what I want to do, and your homework for tonight is section 7.5, 1 through 81 odd. You can skip number 53. I think that had a hyperbolic trig function on there, which we're not covering in this class. Oh, and I should point out, anytime if you see a hyperbolic trig function, you're not expected to know that for a quiz or a test, but if there is one, the formulas for hyperbolic trig functions are in, I think it's section 6.7, I think, something like that. And so you can always look that up to do the problem if one sneaks in there. Anyways, so your homework is 1 through 81 odd in section 7.5. And what you'll see are just a whole bunch of integrals. And these integrals, the instructions don't say use this technique or that technique. They just say compute the integrals, right? So I guess it says evaluate the integral. And so what I'm going to do, I'm just going to write down a few quick examples, and I don't want to compute the entire thing. What I want you to do is think in terms of strategy. When you're handed a particular integral, how are you going to go about doing that? So for example, let's look at this one right here. Integral x times sine x times cosine x. What you see here, all right, this is not one that you've seen. Actually, I think you have seen this on a previous homework, but it's not one of the standard ones that you see. But this is polynomial times trig. When you have polynomial times trig, you immediately want to think integration by parts. Almost always, unless it's been rigged to do some kind of substitution, this is an integration by parts problem. And what do? You let u equal the polynomial part, so u equals x, and dv equals the trig part, sine x, cosine x, dx. Okay, so then when you compute, notice you're going to have to compute the antiderivative to figure out what v is. In computing the antiderivative of sine x times cosine x, you'll have to use substitution. Right, so there's an example. In the process of doing integration by parts, you'll have a substitution problem. So I don't want to carry out the actual integral. You can do these on your own. I want to think about how should you approach a particular integral. This one, we see polynomial times trig. Think integration by parts. Let's see, next one. And obviously, I'm not going to be able to do all of the ones. I'm looking at some of the even ones that are in your book here, and I just want to, let's do this one right here. So cosine of 1 over x divided by x cubed dx. All right, so what do we see? I see some polynomial part, I see some trig part. I'm thinking probably integration by parts might show up. I'm not positive, but it could very well show up. But in this case, I think there's really only one option, and that's to do substitution, where you let u equal 1 over x, then du equals, oh, and you know what? I'm going to call it a different, instead of u, let me call it t. T equals 1 over x. dt equals negative 1 over x squared dx, which means that dx equals negative x squared times dt. So now, when I substitute, let's see what happens. I'll have a cosine of t. I'll have, let me just leave this in place for a minute, an x cubed, and then dx is going to be a negative x squared dt. that's equal to, well, there's a minus sign. Let's pull that outside. Cosine t. And then the x squared and the x cubes cancel and leave me an x dt. So notice I have a 1 over x. This becomes negative integral t cosine t dt. Now we're set up to do integration by parts. So here's another example. In this case, we do a substitution, and it leads us to an integration by parts problem. That's a typical kind of problem that you're going to see. I'm just going to do a few more examples, and it's really just how should we think about it. And it's oftentimes, it's a process of elimination. It looks like it's in the range of this type of problem. For example, when I saw this and I saw trig and polynomial, I was thinking integration by parts, but it's not automatic. Doing a substitution is what converted it to integration by parts. How about, how about this one? So this is integral natural log of x in the top. In the bottom, we've got x times square root 1 plus natural log of x squared dx. Now notice it's got a square root in it, and when you see square roots, you often should think, oh, I wonder if trig substitution is going to come into play. Most likely it is. But first, I mean, it's not quite obvious. I've got these natural logs of x's in here. So let's see what we can do if we let u equal natural log of x, du equals 1 over x dx. And so let's see what we get here. This will be integral u over square root 1 plus u squared. Really? Wait. Huh. Du. I think I got that right. Yeah. Oh, in fact, this is actually easier than I thought. Once I did the first substitution, I see, oh, this one will actually go by doing another substitution. If I let, say, I don't know, t equal 1 plus u squared, notice that the derivative of this will cancel out that. And so this is actually set up to do substitution. So 2 substitutions actually get there. When I saw the square root, I suspected maybe trig substitution, but actually u substitution is the one that will work in this case. All right, so I guessed, but I guessed wrong. So let's just do a couple more examples. And it's really kind of, when you look at these, it's kind of a process of elimination. When you see it, you'll say, okay, is this an integration by parts problem? Possibly or definitely not. Is this a trig substitution problem? Possibly, definitely not. And so by looking at them, you can often rule out certain techniques. Okay, so I want to do one more example. And this one, maybe the trickiest one possible, or trickiest one on here that I can see. And it looks like this, so 1 plus e to the x dx. Now, when you see this one, remember you want to think sort of in process of elimination. This is clearly not a partial fractions, at least not at this moment. It's not a product of trig functions, and so our options are integration by parts, or trig substitution, or u substitution. Right? Those are the 3 that are sort of remain in play. Now, I'm thinking trig substitution, but remember, a trig substitution really needs something of the form, it would need to be something of the form 1 plus something squared. And so that's what I want to do, is kind of set this up or turn this into a trig substitution problem. And the way I'm going to do that is I'm going to let u equal e to the x over 2. Which would then give me a du equals 1/2 e to the x over 2 dx, which is equal to u over 2 dx, which means that dx is equal to 2 du over u. And so now, all I've done is a u substitution so far, and this gives us then square root of 1 plus u squared times 2 du over u. And if we simplify this a bit, we'll get 2 integral square root 1 plus u squared over u du. All right, now we've got trig substitution. And so in this case, it's a tangent substitution. If we let u equal tangent theta, then du equals secant squared theta d theta. And so now when we substitute, we'll have a 2 integral square root of 1 plus tangent squared theta. Underneath, we will have a tangent theta. And then du is a secant squared theta d theta. This part right here is a secant theta. So when we get rid of the square root, what we'll have is a secant cubed theta over tangent theta d theta. So now we've got a product of trig functions, and unfortunately it doesn't fall into any of the categories, our standard categories, and so we just need to try something. And in this case, well, here's what I want to do. I want to peel off, I mean, I do have an odd power of tangent, if you like, but I don't have an even power of secant, but I have an odd power of tangent. And so what I'm going to do is I'm going to peel off a secant and a tangent, right? So this is going to be a secant squared, and then a secant theta, and then I also want to pull a tangent theta off. In doing so, to compensate, what we get is a tangent squared theta in the denominator. Now, if I apply my identity, what do I have there? So this will be a 2 integral secant squared theta, secant theta, tangent theta, d theta. And in the denominator, then this will be a 1, it'll be a secant squared theta minus 1. Right, now we're in position to do substitution where, I guess I already used u, so let's use a t. T equals secant theta. dt equals secant theta tangent theta d theta. And so now we get 2 integral u squared over u squared minus 1 du. Haha. And so now notice what we have. To do this one, you essentially do long division, right? So I'm not going to carry it out any further. Notice what we have. I mean, this comes into our partial fractions section. And so let me think what we did here. We did substitution, which gave us trig substitution, which gave us products of trig. Oh, then I had to do another substitution, product of trig functions, and then and then another substitution, which gave us partial fractions. So this one essentially gave us every single technique that we've learned all in one, which is, kind of funny. So, what can I say? You got a bunch of problems you want to work on. Do those. Come to office hours, ask questions. To learn how to do integrals, you just need to practice. That's the main thing. So practice your integrals, and we will see you next time. Okay? Bye.